Have you ever had a melody in your mind but you don't remember what song it is? What do you do in those cases? Maybe you ask a relative or a friend, but what if you could ask an AI? Imagine if you could just hum or whistle the melody to your phone, and it could finally tell you what melody it is.
Solving this problem has many use cases and applications. Users would provide a sung, hummed, whistled, or instrument-played melody, and the system will identify the closest matches. It could also be used in teaching, perhaps for copyright purposes, or many other musical applications.
Automating music production is not a new challenge. Tools like Sesame have been in the market for more than 2 decades, but they don't recognize notes in melodies. They recognize recordings, so they won't work if you try humming or whistling the melody. Only a few commercial options like Google Home to search or AHA Music take a symbolic approach to extract melody from the user audio input.
I'm Darren Verdisco.
I am Manikandra Padwal.
I'm Israel Romero, and we decided to explore this relatively new space and build a basic melody matching application using artificial intelligence.
Melodies are shaped by pitch contour, timing, duration, and they can be recognizable and memorable when their notes feel like they belong together and transmit emotion.
All these different aspects of a melody can be compared to find similarity. For instance, you can identify the genre, the author, or band playing a melody thanks to the similarities in instrumentation, pitch contour, musical range, etc.
For this project, we'll focus on comparing the similarity between note sequences. This is the comparison that would tell you the song you're looking for. Notes are represented with symbols, either a pentagram or digitally using MIDI technology. MIDI files are a musical file format that contains information about the notes like their pitch, duration, intensity, and many other attributes that capture as much of the human interpretation as possible.
The MIDI interface allows up to 16 different channels assignable to independent instruments and musical parts. So, multiple sub-melodies are played at the same time. This means a single MIDI file could have a digital representation of all the notes played by an entire orchestra.
However, it's typically one instrument at a time that carries the main melody, which is what we tend to recognize and remember the most. Recognizing what instrument or MIDI channel contains the main melody is another problem on its own. So for the scope of this project, we'll assume that the main melody has already been identified.
One easy way to visualize MIDI information is with a piano roll view. These charts show the range of MIDI pitches from 1 to 127 in the vertical axis, while the horizontal axis represents time. The spots represent instances of notes, and their length represents their duration. This is a piano roll of Beethoven's Fifth Symphony.
From the many publicly available MIDI file sources, we've picked a classical music MIDI dataset found on Kaggle, which contains 295 MIDI files of 19 classical and romantic authors, from Bach, Beethoven, and Chopin, to Mozart, Liszt, and Tchaikovsky.
Files are grouped by author in a subfolder structure. This small dataset allows us an in-depth exploration of the melodies. We confirm there are no duplicate melodies in this dataset.
Another advantage of this dataset is that it includes only MIDI files with a single MIDI channel, simplifying our analysis to just one melody identification. Likewise, all the files contain only piano as selected instrument. We will call this the reference dataset.
To enhance our testing capabilities, we scraped the internet in search of alternative versions of the melodies in our dataset. We selected 95 from another dataset called MIDI Classic Music and selected 8 of the composers present in our reference dataset. I also happen to be an amateur musician, so I recorded 18 variations of Beethoven's Fur-Elise using a MIDI synthesizer under different tempos, keys, and rhythmic variations. We'll call this whole alternative collection of MIDI files the testing dataset.
Our plan is to use the reference dataset for training and validation, while our testing dataset will be treated as data non-previously seen by the model, emulating a real user inquiry.
In terms of features, for this project, we will focus only on note pitch and harmonies that make the melody, excluding all other available information in MIDI files.
We learn from the work of other research teams, like Project MelodySim, where researchers used an AI transformer tool called MERT to extract the digital symbolic representations, or embeddings, from audio files. Then, they trained a triplet neural network that learned to determine similarity from those embeddings.
Our primary goal is to take an input melody in a MIDI or WAV format, classify it amongst the available training music data, and provide the name of the identified melody and a similarity score as an output. Lastly, we will use FAISS to index the embeddings and improve the model performance.
First, we establish a baseline, the zero shot, which is using only pre-trained MERT as it comes out of the box. Our hypothesis is that fine-tuning MERT with LoRa adapters would improve MERT's learning ability. Lastly, we'll add a CNN temporal projection head on top of the LoRa fine-tuning, which will add more trainable parameters and enhance the learning capabilities even more.
For testing and fine-tuning, we'll use a melody triplets dataset. Triplets are a combination of 3 melodies. The first one, called Anchor, is used as a reference. The second one, called Positive, is a melody identified to be similar to the anchor. The last one, called Negative, is a melody identified to be different to the anchor. With these combinations, we'll help MERT learning what should be considered similar or dissimilar.
Also, we assume that the final user will likely just hum or whistle a small subset of notes from a melody. For this reason, we decided to split each melody in the training dataset into smaller chunks that can more easily be coupled. Each segment contains 32 notes and overlaps with its labels by 16 notes, starting with 16 notes with the previous chunk and ending with 16 notes from the next.
MERT can only produce embeddings out of WAV audio files, which represents an advantage for a commercial product using our model. For training, we'll convert our reference dataset to audio versions using FluidSynth, a virtual synthesizer that renders a WAV file.
To measure our results, we will use a metric called recall, which tells us how well our model identifies the items it's supposed to find. It focuses on false negatives, which are cases when the model misses the correct melody. High recall means the melody is successfully catching the most relevant items and producing very few false negatives, while low recall means the model is overlooking many similar melodies.
Considering that our application will return a list of our most likely matches to the input melody, we'll measure the recall of the experiment models in 3 ways. Recall at 1, meaning how often the model returns the top match correctly. Recall at 5, meaning that if the correct melody was in the top 5 choices. And for recall at 10, to measure if the correct melody was in the top 10 choices.
Our results are in line with our hypothesis. For the zero-shot experiment, recall at 1 was 45%, while recall at 5 was slightly above 60%, and recall at 10 reached close to 68%. The LoRa fine-tuned MERT got a recall at 1 of 60%, recall at 5 of 73.5%, and a recall at 10 of almost 79%. Lastly, our LoRa fine-tuned MERT plus CNN got almost 64% for recall at 1, almost 78% for recall at 5, and over 83% for recall at 10, maximizing the performance of the model.
This chart illustrates how our final model has a better ability to cluster positive and negative pairs from the triplets dataset compared to the MERT LoRa fine-tuning alone. When testing with previously unseen data, our model underperformed when presented with variations at different tempos, keys, and rhythmic styles of melodies present in the training set. We attribute this large gap mainly to two confounding factors.
First, the validation set was drawn from the same distribution as the training corpus, same MIDI files, just different chunks. We suggest adding more variations to same melodies in the training and validation sets, either by recording, searching the web, or even programmatically.
Second, the FICE index was built exclusively from training corpus embeddings, so the model must breach the acoustic gap. An error analysis of misses at rank 1 shows that the model correctly identifies the composer family, but still confuses specific pieces.
Other areas of experimentation could be increasing the chunk size from 32 notes to 64 or larger with different overlap patterns.
Or using zero-shot similarity scores to filter out triplets with very low positive similarity or very high negative similarity.
Overall, this project exemplifies the potential that transformers and CNNs can have in the world of music, helping artists around the world from assisting their learning path to protecting their creative work from plagiarism, all with the power of AI.